the cosmic scout that changed everything. On October 19, 2017, Canadian astronomer Robert Warwick was reviewing images from the Pan-STARRS 1 telescope on Hawaii's Haleakala Observatory when he spotted something extraordinary: a faint streak racing across the frame at 6.2 degrees per day. That's blazingly fast for any object in our cosmic neighborhood. By the time humans detected it, Oumuamua was already 33 million kilometers from Earth and accelerating away from the sun like it had somewhere important to be. Here's where things got wild. Within days of orbital calculations, astronomers realized this object had an eccentricity of 1.1956. Anything above 1.0 means it's not gravitationally bound to our solar system. This wasn't an asteroid or comet orbiting the sun. This was the first confirmed interstellar visitor ever detected passing through our solar system, and it was already on its way out. The discovery team gave it a Hawaiian name, Oumuamua, meaning a messenger from afar arriving first. That scout brought more mysteries than answers. Shape-shifting mystery. Scientists measured Oumuamua's brightness and discovered something bizarre. The object's light varied by a factor of 10, with a rotation period averaging 8.67 hours. This extreme brightness variation, more dramatic than any known minor body in our solar system, suggested something with a highly unusual shape. Initially, astronomers calculated it had an extreme elongated form, perhaps 8 to 10 times longer than it was wide. Neil deGrasse Tyson offered an intriguing interpretation, suggesting Oumuamua might be a clump of loosely collected rocks, with gravity pulling them into a chain. It's creative and would explain the proportions without requiring exotic materials. But here's the twist. More sophisticated modeling published in 2019 suggests the popular cigar shape might be wrong. The data fits better with a disc or pancake shape, with a 1:6 aspect ratio, because this geometry doesn't require the object to be pointing at Earth with high precision to produce the observed brightness variations. Avi Loeb's analysis indicated that if Oumuamua is disc-shaped, assuming an albedo of 10%, it would have a radius around 100 meters and be remarkably thin, possibly less than a millimeter thick according to some models. Interestingly, Oumuamua was in an excited spin state, with its long axis precessing around its total angular momentum vector. The timescale for damping such excited rotation in a body this size is very long, possibly reflecting a violent ejection from its original planetary system. If you're enjoying this deep dive into one of astronomy's most puzzling mysteries, hit that like button and let me know in the comments what you think Oumuamua really is. And stick around, because we're about to get into the controversial acceleration anomaly that has Harvard professors and the scientific community in heated debates. The acceleration anomaly that broke physics. Here's where Oumuamua goes from interesting to mind-bending. In June 2018, scientists detected that Oumuamua wasn't just coasting on a purely gravitational trajectory. It was accelerating away from the sun with a non-gravitational force, measuring approximately 2.5 micrometers per second, squared at about 1.4 astronomical units from the sun. A micrometer is a millionth of a meter, so this might not sound like much. But the precision required to detect this deviation was extraordinary. Non-gravitational accelerations are typically 3 to 4 orders of magnitude weaker than gravitational forces, making this finding significant. When comets exhibit this behavior, we see them develop a distinctive coma, a bright fuzzy halo of light-scattering dust and gas being boiled off by solar heat. That outgassing acts like a natural rocket engine. The problem? Despite passing within 0.25 astronomical units of the sun, closer than Mercury's orbit and hot enough to vaporize any normal icy comet, Oumuamua showed absolutely no cometary activity. No coma, no tail, nothing. What was pushing it? Theory 1. The hydrogen iceberg hypothesis. The scientific community has wrestled with several competing theories, and this is where things get spicy. In March 2023, Jennifer Bergner from UC Berkeley and astronomer Daryl Seligman published a Nature paper proposing that Oumuamua's acceleration came from hydrogen gas sublimating from its water ice surface. Their idea, as Oumuamua traveled through interstellar space for millions of years, energetic cosmic rays bombarded its surface, breaking apart water molecules to form hydrogen that remained trapped within the ice matrix. When solar heating warmed Oumuamua near perihelion, this trapped hydrogen would sublimate and provide thrust. The elegance of this theory is that hydrogen gas is nearly invisible to telescopes and wouldn't produce the bright dust tail we typically associate with comets. The dust remained embedded in the ice structure even as hydrogen escaped. According to this model, Oumuamua likely started with a fairly normal shape, possibly a 2-to-1 aspect ratio, before losing mass through sublimation. Theory 2. The nitrogen ice fragment. Arizona State University. Astrophysicists Stephen Desch and Alan Jackson propose that Oumuamua is a chunk of an exopluto, a piece broken off from a Pluto-like dwarf planet in another solar system. Their research suggests it's composed of nitrogen ice similar to Pluto's surface, which could survive 500 million years in interstellar space, while reflecting 2/3 of the sun's light. The compelling aspect of this theory is the timeline. Desch and Jackson noted that Oumuamua entered our system at a velocity slightly lower than expected for an object that had been drifting for billions of years. This suggests an interstellar journey of perhaps 500 million years. They calculated that if Oumuamua started with a typical 2-to-1 aspect ratio when entering our solar system, rapid nitrogen sublimation near the sun would have eroded it dramatically. By 1 month after perihelion, it would have lost 92% of its original mass, resulting in the extreme pancake shape we observed. Theory 3. The light sail controversy. Now we reach the theory that ignited astronomical debate. In October 2018, Harvard astronomer Avi Loeb and postdoctoral researcher Shmuel Bialy submitted a paper exploring whether Oumuamua could be an artificial light sail accelerated by solar radiation pressure. Loeb's argument centered on unusual coincidences. The measured acceleration requires an extremely large surface area to mass ratio, suggesting Oumuamua would need to be roughly a millimeter thick. That's extraordinarily thin for any natural rocky object. He calculated that if composed of rock and iron, similar to Earth's density of 5,500 kilograms per cubic meter, the thickness would be between 50 micrometers and 1 millimeter, depending on its actual area. That's paper thin in cosmic terms. Additionally, Loeb noted that Oumuamua's velocity closely matched the local standard of rest. The average motion of nearby stars in our Milky Way arm, only about 1 in 500 stars, sits so close to this rest frame. For an object designed to visit multiple star systems without revealing its origin, this would be strategically ideal. The scientific community's response? Largely skeptical. Most astronomers stated the evidence was insufficient to seriously consider artificial origins, noting that a tumbling solar sail couldn't accelerate properly anyway. The anomalous properties could be explained by exotic but natural compositions. However, Loeb maintains his position, detailing his arguments in his 2021 book, Extraterrestrial: The First Sign of Intelligent Life Beyond Earth. The data we actually have. Let's talk hard numbers, because separating speculation from observation is crucial. Based on brightness measurements and assuming a cometary albedo of 4%, Oumuamua is estimated to be roughly 800 by 80 by 80 meters. However, different albedo assumptions yield different estimates. NASA's analysis suggests it's up to 400 meters long, while Spitzer Space Telescope observations, which failed to detect its infrared signature, constrained its spherical diameter to somewhere between 100 and 440 meters, depending on composition assumptions. The object displays a reddish color, consistent with surfaces exposed to cosmic ray bombardment over hundreds of millions of years. This coloration resembles objects in our outer solar system and suggests a composition of rock and possibly metals. Notably, no water ice was detected on its surface. Oumuamua passed perihelion on September 9, 2017, at just 0.25 astronomical units from the Sun, inside Mercury's orbit, where temperatures should have triggered massive outgassing from any normal comet. Its outbound trajectory is inclined about 20 degrees above the ecliptic plane. Orbital calculations suggest it came from the approximate direction of the bright star Vega in Lyra, though Vega's stellar motion rules it out as the actual source. The object's velocity aligns closely with the local standard of rest, the average motion of stars in our Milky Way neighborhood, making it difficult to pinpoint a specific origin system. It's been wandering interstellar space for hundreds of millions of years. Why we missed it until the last second. Oumuamua's trajectory brought it from above the solar system's ecliptic plane, an unusual approach angle for near-Earth object surveys like pan-stars. Shortly before discovery, it had just emerged from solar conjunction, hidden behind our star. Astronomers don't typically point telescopes that close to the sun for obvious reasons. Additionally, its small size made it inherently faint. Even Hubble couldn't have detected it earlier in its approach. The discovery itself benefited from recent improvements to pan-stars' one's detection pipeline, which increased efficiency at finding trailed objects that were previously rejected as spurious detections. By discovery time on October 19, 2017, Oumuamua was already 40 days past perihelion and receding at 85,700 miles per hour, 38.3 kilometers per second. Relative to the sun within a week, its brightness dropped tenfold. Within a month, it had faded 100-fold. Astronomers had an extremely narrow window to gather data on this unprecedented visitor. It passed Mars's orbit by early November 2017, Jupiter's orbit by May 2018, and crossed beyond Saturn by January 2019, now forever beyond our telescope's reach. Could we have caught up to it? Chasing Oumuamua presents a monumental engineering challenge. It's moving 2 to 3 times faster than conventional chemical rockets can achieve. While some proposed missions to intercept it, such endeavors would cost over $1 billion and require innovative gravity assist maneuvers from multiple planets while pushing propulsion systems to their absolute limits. Interestingly, if Oumuamua were actually a light sail as Loeb proposed, calculations show it would have a terminal velocity around 610 meters per second. At that speed, it would take approximately 2 million years to reach our nearest stellar neighbor, Proxima Centauri. That's hardly the relativistic speeds you'd expect from advanced alien technology, which provides one of many reasons most scientists remain skeptical of artificial origins. What Oumuamua tells us about the universe. Oumuamua's discovery revealed that previous estimates of interstellar object density were pessimistically low. Scientists now calculate there's always roughly one interstellar object around 250 meters in diameter. Within 1 astronomical unit of the sun, they're constantly passing through, invisible until our technology improved enough to spot them. Pan-STARRS began operations in May 2010, and models predicted it might detect few, if any, interstellar objects larger than 1 kilometer during a decade of observation. Finding Oumuamua so quickly suggests these cosmic wanderers are far more common than anticipated. Charles Liu, an astrophysics professor who collaborated with Neil deGrasse Tyson on multiple publications including One Universe at Home in the Cosmos, has emphasized throughout his career how studying material from outside our solar system provides insights impossible to gain from Earth-based observations alone. Oumuamua represents exactly this opportunity, a chance to examine matter that formed around a completely different star with potentially different chemistry and formation conditions, teaching us about planetary system diversity across our galaxy. The impact on Earth science. Oumuamua's discovery introduced a new dimension to Earth's impact risk assessment. Impacts from interstellar objects would be far more energetic than solar system collisions due to much higher velocities. Meteorites from such events would display ages inconsistent with our 4.5 billion-year-old solar system, though no such specimens have been identified to date. This fundamentally changes our understanding of cosmic threats. We've spent decades tracking near-Earth asteroids and comets, all moving at predictable solar system speeds on calculable orbits. Interstellar objects arrive from random directions at dramatically higher velocities. It's the difference between monitoring traffic on a highway versus watching for meteorites. One follows predictable paths, the other can materialize from anywhere, with little warning. What happens next? The Vera C. Rubin Observatory, which recently began operations, is expected to detect roughly 1 Oumuamua-like object per month. This will provide an unprecedented dataset. Instead of one mysterious visitor glimpsed for weeks, we'll accumulate dozens or hundreds of interstellar objects to study, compare, and analyze over coming years. This observatory produces approximately 20 terabytes of data nightly. According to astronomer Karen Meach, had it been operational in 2017, it could have detected Oumuamua in late July, 3 months before pan-STARRS, giving astronomers time to observe its perihelion passage and gather far more comprehensive data. With sufficient examples, patterns will emerge. We'll determine whether Oumuamua was genuinely anomalous or fairly typical of interstellar debris. we'll see if other objects show similar acceleration, anomalies, shapes, and compositions. This statistical approach will either validate existing theories or force completely new hypotheses about what travels between the stars. So what is Oumuamua? After thousands of observation hours, hundreds of scientific papers, and years of debate, the honest answer remains. We don't definitively know by mid-2019. Most astronomers had concluded it was natural, but its precise characterization remains contentious, given our limited observation window. The hydrogen ice theory currently leads in peer acceptance, explaining the acceleration without exotic materials or unprecedented compositions. The nitrogen ice theory elegantly fits the data, though it requires substantial mass loss during Oumuamua's solar encounter. The light sail hypothesis exists, but remains the most controversial and least accepted explanation among professional astronomers. What we know with certainty, Oumuamua was genuinely unprecedented in modern astronomy. It provided our first confirmed glimpse of material from another star system, tumbling through our cosmic neighborhood. Whether it's an exo-Pluto fragment, a hydrogen iceberg, or something else entirely, it represents a revolution. The ability to study extrasolar material without leaving our solar system. The universe just became significantly more accessible and infinitely more intriguing. If you loved learning about Oumuamua and want to stay on top of all the latest space discoveries, do me a solid and smash that subscribe button. We're covering everything from black holes to the search for alien life. And trust me, the cosmos is only getting weirder from here. See you in the next one, space fans.